All right, we're going to begin with the counting principles in section 9.6. And we're going to start with a real basic idea. We've got 8 pieces of paper that are numbered 1 to 8, and they're placed in a box. One piece is drawn from the box. You write down the number, put the paper back in the box, pick up a second piece, and add the 2 numbers together. We want to figure out how many different ways can we get a sum of 12. All right? I want you to take just a second or two and think about how many different ways. You may want to jot it on your paper and then we'll discuss it. But think about how many different ways, if you draw one piece of paper, write down the number, put the piece of paper back in the box. Draw another piece of paper, write down the number. How many different ways can you get a sum of 12? Okay, let's talk about it. Miguel, how many ways did you come up with? You came up with 5. Lewis, how many ways did you come up with?
36. 12. 36.
12. Noah, what did you get?
3.
3. Adam, you're 3. Colleen? 5. Taylor?
First I got 3. That's what I thought.
3.
Oh yeah.
Okay, so let's talk about the different ways that you came up with your different numbers. Lewis, let's see. Lewis, how many did you tell me?
No, wait, I messed up. 12.
Noah, how did you get 3?
Well, I wrote all the numbers down on the paper, and then I erased the ones that couldn't get a sum of 12, and then I was left with 4, 5, 6, 8, and 7.
Okay, so you thought let me 4, 5, 6, 8, and 7. Now, what are those numbers?
Numbers that could be used to make a sum of 12.
Okay, numbers that could be used to make a sum of 12. So how did you get 3?
4 plus 8,
Okay.
12. 5 plus 7 is 12. And 6 plus 6 is 12.
Okay, so that's how you got 3. How did you get 5, Miguel?
I put that ones.
Mm-hmm.
I put 8 plus 4. 7 plus 5.
Okay, now let's go back and read the question. You pick up one piece out of the box, you write it down, and you put it back in. And then you draw a second piece. And then you add them together. Which way's correct, do you think? 3 or 5?
5.
Okay, I'm seeing several full hands up. So 5. 5 is the correct answer for that. Because here you could get 4 the first time and 8 the second time. Or you could get 8 the first time and 4 the second time. So those are 2 separate instances that would give you 12. So in this case, we get 5 different ways. All right? That didn't work, so I'll tell you. How many ways can a computer randomly generate 2 integers from 1 to 12 whose sum is 6? Okay? How many ways can it randomly generate 2 integers from 1 to 12 whose sum is 6? Okay, think about that for a minute, and then we'll talk about how many ways a computer can generate 2 integers from 1 to 12 whose sum is 6. All right, how many different ways can we get 2 integers whose sum is 6 if we're only using numbers 1 to 12? Lewis? 5. Miguel? 5. Corbin, what do you think? 3? Trey? 5. 5 seems to be a consistent answer. If we use 5, Miguel, what are the combinations?
1 plus 5.
Mm-hmm.
2 plus
plus 4, 3 plus 3, 5 plus 1, 4 plus 2.
Does anybody disagree with that? Are there any additional combinations that we could come up with that would give us 6? In a situation like this, does the order matter?
No.
Yes.
Well, and I guess that's not a very good question. It's randomly generating numbers. So you're going to get a first number and a second number. So notice here, we have 1 plus 5 and then 5 plus 1. They each count as a separate event. So I'm not sure if you'd say order matters or order doesn't matter in this case. I guess order does matter. Because this gives us one possibility, this gives us another possibility because it's in a different order. Okay, what happens here if we want distinct pairs?
Would 1 and 5 and 5 and 1 be distinct? Or?
Yeah, would they? Would 1 plus 5 and 5 plus 1 be distinct?
Yes.
Okay, what would not be distinct? Or is there anything that would not be distinct here? 3 plus 3. So if we were looking for distinct pairs, we would have only 4. If we go back and look at the previous,
You mean 30?
we'd have 1, 2, 3, 4. Because it's still, 1 plus 5 is distinct from 5 plus 1.
1, 2 plus 4, and 4 plus 2.
Those are distinct from each other. So we'd have 4. Did I say something different?
No,
Okay. This is the one that we'd have to eliminate
Oh, okay.
because it's the same number. Let's look at the previous question. We had 5 ways that the numbers could be obtained to get a sum of 12, but what if the 2 pieces are drawn at the same time? We don't put the one piece back in, the first piece back in, but we draw them with separate hands at the same time. How many possible ways could you get a sum of 12 there?
4, it just takes away the one with the same numbers.
Yeah.
Good. Takes away the one with the same numbers because you can't possibly, if you're picking them both up at the same time, you can't get 3 twice. So in this case, if we wanted to have no replacement, then we only have 4 possibilities. So really, the difference between those 2 situations, first we were looking at with replacement, and then when I said we chose them both at the same time, we were looking without replacement. And so that can make a difference on the outcome of our number of possibilities that we come up with. If you can, it's always a good idea to list your possible events, just like you did on that second one. We had 1 plus 5, 2 plus 4, 3 plus 3, 5 plus 1, 4 plus 2. If you can do that, it's good. But obviously that's not always a possibility for us to do that. Okay? All right. You probably will need a calculator because the numbers are getting bigger, and even though it's good for us to be able to do some of this without a calculator, I don't want to take the time in class. So this asks us how many different pairs of letters from the English alphabet are possible. How many different pairs of letters from the English alphabet are possible? Take a second and see if you can figure out how we might try to work this. Okay, so how many different pairs of letters from the English alphabet are possible?
606.
Trey says 676. Does anybody have something different than 676? Kelly?
I got 650.
You got 650. So we've got a 676, a 650. Anything else? How did you get 676, Trey?
26 times 26
And why did you do that?
is every letter can be matched up with one of the other 26 ones.
Okay. So 26 possibilities for the first one and 26 possibilities for the second one. How did you get 650, Kelly?
I did 26 times 25.
Okay, and why did you choose to do it that way?
Because it says different pairs, so you can't do like A and A, you have to, like, if you match them all up, it would be 25. Because you can't do a letter with itself.
Okay,
Depends on how you read the problem.
Yeah.
Okay, that makes sense.
so I'm hearing that makes sense. Which do we think this is?
But it's still a pair of a letter if it's A and A.
But it's not different.
A and A is in
No,
it's
it's
different.
different than the pairs.
Oh,
Okay, Trey, would you say that again?
It said A and A is different pair than A and B.
So which do we think?
676.
Colleen says 676. Adam, which way do you think?
I agree with
You agree with Colleen? Okay. Kelly, I like your reasoning, but I'm afraid I have to agree with Trey on this one.
Okay.
All right? We have a possibility of 26 letters the first time, and then a possibility of 26 letters the second time. All right, so that leads us to the fundamental counting principle. And I'm going to go ahead and tell you what that is. All right, so what we just saw was an example of the fundamental counting principle, where we have two different events. I can't spell today. And this is one of those principles that can come in real handy. I hope that you all are getting ready to start taking your SATs. And so there's almost always counting problems, probability problems. So this is one of those principles that you want to remember. The fundamental counting principle says, okay, we've got two events. We've got event 1 and we have event 2. Event 1 can occur in M1 ways. And event 2 can occur in M2 ways. Just like we looked at with the alphabet. Event 1 was that first letter, the first part of the pair. Event 2 was the second part of the pair. All right, so the first 26 was M1. We had 26 options for the first part of the pair, and we had 26 options for the second part of the pair. The number of ways, and let me stop just a second. The number of ways that the two events can occur, the number of ways the two events can occur is M1 times N2. And you already figured that out with that alphabet problem. M1 times M2. Okay, so we've got this combination lock that will open when the right choice of 3 numbers is selected. How many combinations are possible? Corbin, how many did you get?
Is it 2,700?
2,700? John, what did you get?
I got 27,000.
Colleen, what did you get?
27,000.
27,000. Kelly?
I don't do it. I don't know how to do it.
All right. How many different numbers are we looking for?
I got one.
How many different? 3 of them. Okay, what did you get?
I got 26,970.
26,970. Okay, yes.
I got 451.
450? 450.
All the way around when you do it.
Because you have to,
Okay, how did you get 450?
I guess you could.
Shh.
Probably wrong, Heidi, but, since it's a three choices,
Mm-hmm.
I figured out that,
Yeah, you can spend it all the way.
oh, wait a minute, that'd only be one, never mind, I realized.
Okay. How did you get 26,970?
I said that you can't do 1, 1, 1 or 2, 2, 2, but you could actually spin it all the way around. So it would be 27,000.
You think 27,000? You vote for 27,000?
I just thought of it as a log, like, instead of the ones that you spin, the ones that has like the three kind of different little knobs. 1 through 30, that's the way I.
Okay. Now, Kelly, let's think about this. How do we find the number of possible combinations here? What was our rule for the fundamental counting principle?
M1 times M2.
All right, but this time we don't have just 2 possibilities here, we have 3. So, how many possibilities do you think there are for filling in that first number of the combination?
30.
30. How many possibilities are there for filling in the second number of the combination? 30. Are you starting to see?
Yeah,
All right. And for the third?
30.
30. Okay. Corbin, did you just give me the wrong number?
Yeah.
I thought maybe that's what was happening. Okay. Oops. Okay, so are we okay on that, Kelly? So this does give us 27,000. Show us what you did, Luke.
Okay. Well, since there's 7 possibilities, but the first one can't be 0 or 1, I just, I like how the book drawed it is. There we go. So for this digit, there's only 8 possibilities. For this one, there's 10. This one, 10. No dash. 10. 10. 10. And when you multiply all that,
Oh, nice.
it is 8 million.
Very good.
No.
You got enough there? There are times that we want to determine the number of ways that elements can be arranged. And if we have an ordering of n elements, the number of ways that they can be arranged, if we have an ordering, we call that a permutation. A permutation of n elements is an ordering of the elements such that you've got one element first, another element second, another element third. So a permutation is an ordering of n elements. Such that one element is first, another is second, and so on. Okay, so that's a permutation. Order matters with permutation. And so if we wanted to know how many permutations are possible for A, B, C, D, E, F, and so it was 6 times 5 times 4 times 3 times 2 times 1, which is an example of 6 factorial. Okay, and how many ways can 8 children line up in a row? You find out how many ways 8 children can line up in a row. Kelly, what'd you get?
I don't have a calculator, but I did 8 times 7 times 6. 5
Okay.
times
So this is an example of a permutation. You could have 8 possibilities for the first place, 7 for the second, 6 for the third, 5, 4, 3, 2, 1. And so I think that's what did you get, Tim?
40,320.
40,320. And that's a case when that factorial key comes in real handy. All right, let's think about it. Okay, got 8 horses running in a race. And how many different ways can they come in first, second, and third?
50.
And how many different ways could they come in first, second, and third? How many different ways can they come in first, second, and third?
336.
336. Do we get something different than 336? 48. Who said 48? How'd you get 48?
I did a permutation of 3, and I multiplied that by 8.
Okay. And why did you do that?
Because there were 3 options, first, second, and third, and there were 8 things that failed it.
Okay. Does that seem reasonable? I'm seeing some wobbly heads. Okay, Colleen, how many horses, what are the number of possibilities for first place?
8.
8. What are the number of possibilities for second place?
7.
And for third place?
6.
Okay, and so see, you did know how to do it. So 336 is the correct answer. There were 8 possibilities for first, 7 for second, and 6 for third. All right, this is an example of a permutation that takes n elements r at a time. Okay, an example of a permutation that takes n elements r at a time, and this is the designation for n elements r at a time. We had 8 elements 3 at a time in this particular situation that we just looked at. We had 8 horses, but we only wanted the first 3 that came in. So that's n elements r at a time. And for NPR, the formula is n factorial over n minus r factorial. So if we were going to go back and look at this, if we look at 8p3, this is going to be 8 factorial over 8 minus 3 factorial, which is 8 factorial over 5 factorial. Okay. 8 factorial is 8 times 7 times 6 times 5, and I'm just going to do 5 factorial because we've got 5 factorial on the bottom. And these cancel out. So 8 times 7 times 6 is what you end up with. Now, again, in your calculator, you have, under math, go to probability, and one of those numbers down there has NPR, and so that is a possibility. In permutations, order is important. Okay, and I messed up that, but we want to know how many distinguishable ways can the letters in banana be written. And if we're looking for distinguishable permutations, the formula is n prime over n sub 1 prime, or factorial, n sub 2 factorial, n sub 3 factorial, all the way down to n sub k factorial. And that's in a situation like this. We have, with banana, we've got 1, 2, 3, 4, 5, 6 letters. So we're going to have 6 factorial. We have 2 of them, or 3 of them that are A's. So that's going to be 3 factorial. 2 of them are N's. And 1 of them is a B. And so that's what the n sub 1 means, the number that are the same. We want n sub 2 is the next number that are the same. You understand where those came from? Okay, so in this case, we have 6 times 5 times 4 times 3 factorial over 3 factorial, 2 factorial, 1 factorial. Well, 3 factorial cancels. 2 is just 2 times 1, and 2 goes into 4 twice. So this becomes 6 times 5 is 30 times 2 is 60 different distinguishable ways that the letters in banana can be written. Yes, ma'am.
How come on the top you only go to 3?
Are you
Not
sure?
2 times 2 and times 1.
Because I knew I had 3 factorial here, and that's, if I did 3 times 2 times 1, it's going to cancel out, so I just stopped where the first factorial on the bottom was. Okay, find the number of distinguishable permutations of this conglomeration of letters. 241, 920. What did you get, Tim?
15,120.
What did you get, Taylor? Yeah, that's what you got. Kelly? Oh, you don't have a calculator. What did you get, Colleen? 15,120? Okay, so, Taylor, how did you put your formula together?
I put 9 on the top, and then I put 3, 2, 2, 1, 1.
Okay, 3 factorial. What did that represent?
That represented the 3 E's,
And the 2 factorial,
represented 2 A's,
and another 2 factorial.
represented the other 2 P's.
Okay.
1 and 1, but nothing.
Okay.
And then I
Did you forget to put these on the bottom tray, or?
I did it like that.
Okay, but something didn't translate when you, okay. We'll look at it in a minute and see maybe what happened. Okay, so then what?
And then I put 9 times 8 times 7 times 6 times 5 times 4 times 3. And the 3's canceled, and the 2 2's canceled the 4.
Okay, so the 3 factorial, this canceled here. This was, so we have 9 times 8 times 7 times 6 times 5, and that does equal 15,120. You see what, did you figure out maybe what you did wrong?
I did it like with the exclamation marks on it.
Okay, I'll look at it in a minute if you still have it in there. All right, your assignment is on page 696, 1 to 4, and then 8 to 26 even.